So, the objectives of this lesson are to introduce basic thermodynamic concepts, state laws of thermodynamics and apply them to closed and open systems, introduce internal energy, enthalpy and entropy, define heat engines, refrigerators and heat pumps and obtain expressions for Carnot efficiency of these devices. And at the end of the lesson, you should be able to define various thermodynamic concepts, identify point and path functions, apply first law of thermodynamics to closed and open systems, and define heat engines, refrigerators and heat pumps and find their theoretical maximum efficiency, and define important properties such as the internal energy, enthalpy and entropy. So, why do we need to do the review? We know that refrigeration and air conditioning deals with several processes which involves transfer of mass, momentum and energy, and all these transfers are subjected to certain fundamental laws of thermodynamics, heat transfer and fluid mechanics. So, in order to understand this particular subject, one needs to know the basics of these three subjects. One is thermodynamics, fluid mechanics and heat transfer. I assume that you have already studied these subjects. So, here the purpose is not to give a very detailed description of all these subjects because it is not possible. So, we quickly run through the basic concepts of thermodynamics, fluid mechanics and heat transfer. So, for any detailed discussions you must refer to a standard textbooks on these subjects. So, let us start with thermodynamics. Thermodynamics is the study of energy interactions between systems and the effect of these interactions on the system properties. So, we define little later what do we mean by system and how do we define properties and all. It is very important to note that thermodynamics basically deals with energy interactions. Since energy interactions exist all over the universe, thermodynamics is a very fundamental and most important subject in engineering. And thermodynamic systems, generally the subject of classical thermodynamics deals with systems in equilibrium. What do we mean by equilibrium? Normally equilibrium means a condition of balance between opposing factions. If you have a thermal equilibrium, for example, if I say that a system is in thermal equilibrium, that means there are no temperature gradients inside the system, so that there is no net heat transfer inside the system. So, you call that as the system in thermal equilibrium. A system is said to be in mechanical equilibrium if there are no imbalance of forces inside the system and there is no net acceleration. So, you call that system as under mechanical equilibrium. And you can also call a system as in phase equilibrium if there are no phase changes taking place within the system. Similarly, you can also have a system under chemical equilibrium when there are no chemical reactions taking place inside the system. And for a system to be in thermodynamic equilibrium, it has to satisfy all these equilibria. That means for the system to be in thermodynamic equilibrium, it has to be in thermal equilibrium, it has to be in mechanical equilibrium, it has to be in chemical equilibrium and it has to be in phase equilibrium. So, classical thermodynamics basically deals with systems in equilibrium. And energy transfer we will see little later. Energy transfer between systems takes place in the form of heat and work. So, let us now define systems. What do we mean by thermodynamic systems? So, a thermodynamic system is defined as a quantity of matter of fixed mass and identity upon which attention is focused for study. So, here you have to notice that the system means generally the mass is fixed and the identity is also fixed. So, in very simple terms, a thermodynamic system is whatever we want to study. So, it can be as simple as a gas in a closed vessel or it can be as complex as a nuclear power plant. So, depending upon the problem, the complexity of the system will be varying. And everything external to the system is called as surroundings. So, you have a system and everything external to the system is surroundings. And generally a system is separated from its surroundings by what is known as a system boundary. And in any thermodynamic problems, it is or any thermal engineering problems, it is very important and in fact it is the first step to choose and identify the system properly and show the boundaries. That means there should not be any ambiguity as far as the system and its surroundings are concerned. Now, thermodynamic systems can be classified into three types. You can have closed systems, open systems and isolated systems. A closed system can have energy interactions with the surroundings, but it cannot have any mass interaction. That means no mass can enter or leave the system, whereas energy can enter or leave the system. Such a system is called as a closed system. In an open system, you can have both energy as well as mass interaction. That means mass can enter or leave the system, energy can enter or leave the system. So, that kind of a system is called as an open system. An isolated system cannot have any interaction. That means neither mass interaction will be there nor energy interaction will be there. That kind of a system is known as an isolated system. Let me give you an example. If you let us say that we have a room, a perfectly insulated room with tightly shut windows, doors, etc., so that no energy can enter into the room and no air can enter or leave the room. And if you take the air inside the room as the system, then it becomes an isolated system, because neither air can enter nor any energy can enter into the room. Now, if you remove the insulation, then even the mass cannot enter. Some heat transfer can take place across the walls. Then the system becomes a closed system, because even the mass cannot enter or leave. Energy can enter or leave by the way of heat. So, it becomes a closed system. Now, if you keep the doors and windows open so that energy can also enter and air also can enter and leave, then it becomes an open system. This is a simple example of closed, open and isolated systems. Now, a control volume is defined as a specified region in space upon which attention is focused. So, control volume can be thought of as an open system where mass can enter or leave, and a control volume is separated from its surroundings by what is known as a control surface. Now, let us define a process. A process is defined as the path of thermodynamic states which the system passes through as it goes from an initial state to a final state. And a cycle is defined as a system is said to have undergone a cycle if, beginning with an initial state, it goes through different processes and finally arrives at the initial state. That means the system passes through several processes in such a way that it finally arrives at the same initial state. So, initial state and final state will be same. So, such a process is called as a cycle. And understanding the nature of the process path is very important, because we will see subsequently that the heat transfer and work transfer depend very much on the process. So, we have to know what kind of a process is taking place. Now, let us define heat. So, in thermodynamics, heat is defined as a form of energy that is transferred across the boundary of a system at a given temperature to another system or surroundings at a lower temperature by virtue of temperature difference between the two systems. So, heat is energy in transit. And how does the energy transfer takes place? It takes place because of the temperature difference. So, if any energy transfer which involves temperature difference is called as heat transfer. And there are three fundamental modes of heat transfer. They are conduction, convection and radiation. Now, let us define work. In thermodynamics, work is said to be done by a system if the sole effect on the surroundings could be the raising of a weight. So, one thing you must notice here is it is not necessary to call something as work only when a weight is raised. Weight need not be raised, but the sole effect could be the raising of a weight. So, this is the thermodynamic definition of work, and again you can have mechanical modes of work and non-mechanical modes of work transfer. So, let us look at mechanical modes of work transfer. The classical modes are moving system boundary work, rotating shaft work, elastic work and surface tension work. And modes of non-mechanical work are electrical current flow, magnetization work and chemical work done during chemical reactions. These are some of the examples of non-mechanical modes of work. Now, let us look at one of the most important modes of work, that is what is known as moving system boundary work. For example, the work done at the interface of a piston and cylinder. Piston is moving and some work is being done in that process. So, this is what is known as a moving system boundary work, if you are considering the gas inside the cylinder and piston as a system. And for such a process, the work done is given by integral PdV, where P is the pressure acting and dV is the small differential volume. So, if you want to find out what is the work transfer during this process, you have to integrate it between the initial and final states. Now, this is subject to an assumption that the process is a quasi-equilibrium process. Now, what do we mean by a quasi-equilibrium process? A quasi-equilibrium process is one which moves very slowly, that at every point you know its state exactly. That means you know its properties at every point, its path is well defined. Such process is called a quasi-equilibrium process. Now, if you do not assume the process to be quasi equilibrium process, you cannot perform the integration, because you do not know what is the relationship between P and V during the process. So, in order to perform the integration, you must know the relation, that means the path must be known. So, this equation is for under this assumption. And to find the work done, as I said, we need to know the relationship between P and V during the process 1 to 2. Now, what is the sign convention followed? Generally in thermodynamics, the sign convention is like this: if work done by the system is considered to be positive and work done on the system is negative. And as far as heat transfer is concerned, heat transfer to the system is positive and heat rejected by the system is considered to be negative. So, as far as possible, we will be following the same sign convention throughout this course. Now, let us define thermodynamic functions. Thermodynamic functions can be either point function or a path function. A point function depends only on the state of the system and it does not depend on the history or path of the system. That means, it depends only on the initial and final states, it is independent of the path. An example of point function is temperature, pressure, density. These are all the examples of point functions. Now, let us look at path function. A path function depends on the path of the system by which the system has arrived at a particular state. That means, in order to evaluate the path function, it is not enough to know the initial and final states, you also need to know what is the exact path taken by the process. So, you need to know the initial and final states as well as the path. Let me show the example. This figure here shows on PV you have volume on the x axis and pressure on the y axis. A system has undergone a process and during this process its state has changed from 1 to 2, and this change of state has occurred by two processes, process A and process B. And for both the processes you will notice that the change in volume is same as 3 meter cube for process A as well as process B. So, we volume here is a property. Since it is a property, it is not dependent on path. For process A or B or for any other arbitrary process, the difference in volume is same. Whereas the work done, for example, the work done in process A is 8 kilojoules, whereas the work done in process B is 12 kilojoules. That means, the work done depends not only on the initial and final states, but also on the path, since it is depending on the total process from 1 to 2. So, you can say that volume is a point function and work transfer or work done is a path function. Now, thermodynamic property. Let us define thermodynamic property. A system is generally specified and analyzed in terms of properties. And a property is any characteristic or attribute of matter which can be evaluated quantitatively. So, this is the exact definition of property, and a property depends only on the state of the system. That means, property has to be a point function. So, all properties are point functions, and one of the peculiar characteristics of a property or point function is that their cyclic integral is always 0. So, this is one of the characteristics of properties. And properties can be either intensive or extensive. An intensive property is independent of mass, whereas an extensive property is dependent on mass. So, what are the examples of intensive properties? Temperature, density, these are the properties which we call them as intensive properties, because they really do not depend on the mass. For example, you take a mass of 1 kg and let us say that it has a temperature of 30 degrees. So, if you divide that mass into 2 parts, still the temperature of each part will be 30 degrees, it does not become half. So, the temperature is an intensive property. Other intensive properties are pressure, density, etc. Okay. And extensive properties are dependent on mass, and one of the examples of extensive property is mass itself or volume. For example, if you have the mass, then volume also becomes half. So, mass, volume, etc. are extensive properties, and you can convert extensive properties into intensive properties by dividing with mass. This is what is known as specific properties. For example, volume is an extensive property, but specific volume, which is nothing but volume per mass, is an intensive property. Now let us state a very important postulate called as state postulate. This state postulate says that the number of independent intensive thermodynamic properties required to specify the state of a closed system, that is subject to conditions of local equilibrium, exposed to n different non-chemical work modes of energy transport and composed of m different pure substances is n plus m. So, basically we use the state properties to find out how many degrees of freedom are required to uniquely fix the state of any system. So, this is the usefulness of state postulate. Let us apply this state postulate to what is known as a simple system. Now, what do you mean by simple system? Let us take a pure substance, a single pure substance. So, m is equal to 1 and it is subject to, let us say, only one work mode, that means n is equal to 1. So, how many degrees of freedom are there? M plus n is 2. So, you have to specify 2 intensive properties to uniquely fix the state of this particular system. Such a system is called as simple system, and an example of a simple system is a pure gas or vapor under compression or expansion inside a piston cylinder, for example, is an example of a simple system, and here the work mode is a moving system boundary work. Now, let us discuss the fundamental laws of the thermodynamics. There are basically 4 laws of thermodynamics: the zeroth law of thermodynamics, first law of thermodynamics, second law of thermodynamics, and third law of thermodynamics. These are the most important laws of thermodynamics, and they are not mathematically derived equations or anything. They are based on our observations of natural phenomena. People have been observing the nature and natural phenomena for centuries, and based upon the observation they have arrived at these 4 basic laws. So, they do not have any mathematical proof. Then how do we know that they are right? We assume them to be right because so far nobody has observed any violations of these laws. Since we have not observed any violations of these laws, we take them to be true. And these 4 laws define important thermodynamic properties. For example, the zeroth law defines temperature, first law defines internal energy, second law defines entropy, and third law can be used to obtain absolute entropy values. So, now let us see these 4 laws. Let us start with zeroth law. The zeroth law of thermodynamics states that when 2 systems are in thermal equilibrium with a third system, then they in turn are in thermal equilibrium with each other. That means, let us say that there are 3 systems A, B, C. A is in thermal equilibrium with B, B is in thermal equilibrium with C. That means, A will be in thermal equilibrium with C. So, this is the simply the zeroth law of thermodynamics. It may look simple, but it is very useful because you can draw one conclusion out of this. When the 3 systems are in thermal equilibrium, there must be at least one property which is common to all these 3 systems. That property is known as temperature. Okay. So, that is how the zeroth law of thermodynamics by way of thermal equilibrium defines a property called temperature, and this zeroth law is the basis for temperature measurement, for example, using thermometers, etc. Now, let us look at first law. First law actually is a statement of law of conservation of energy, and also according to the law, heat and work are interchangeable. That means, you can convert heat into work or vice versa. And any system that violates the first law, or that means which creates or destroys energy, is known as a perpetual motion machine of first kind, or PMM1. And it has been observed that PMM1 does not exist. That means, people have even though they have made several attempts, nobody could create a perpetual motion machine of first kind which can create energy or which can destroy energy. Since nobody could succeed, we assume that it cannot exist. That means, the violation of first law cannot exist. So, first law must be true. So, this is the logic. Now, let us apply the first law for a system undergoing a cyclic process. So, for a system undergoing a cyclic process, you can write the first law of thermodynamics as cyclic integral of dou q is equal to cyclic integral of dou w. Here, what is dou q? Dou q is the net heat transfer during the cycle, and dou w is the net work transfer during the cycle. Now, the same equation can be written in the form as cyclic integral of dou q minus dou w is equal to 0. So, what do we conclude out of this? This means that since the cyclic integral of dou q minus dou w is 0, that means dou q minus dou w must be a point function, because for all point functions the cyclic integrals are 0. So, dou q minus dou w is a point function, that means it must be a property of the system. So, this property is known as internal energy. So, that is how the first law defines a property called internal energy, and you can write the change in internal energy du as dou q minus dou w. And what is physically, what do we mean by internal energy? Internal energy represents a sum total of all energy forms of the system, for example thermal, nuclear, atomic, vibrational, rotational, etc. Now, let us apply the first law of thermodynamics for a closed system undergoing a process 1 to 2. Let us say that a system has undergone a process 1 to 2. So, what is the first law of thermodynamics for that?